In this section, we're talking about, well, we're going to start off talking about how to find an inverse of a matrix. And to find the inverse, there's a very complicated by hand way, which we won't look at all. Instead, we're going to give it straight to the calculator. The calculator will figure it out for us. And the importance of finding an inverse matrix, as it's called, is it helps us with a branch of math called cryptography. So we'll talk more about cryptography here momentarily, but before we begin that discussion, we need to talk about how to find an inverse matrix. And so this is this whole process starts off the same way as in the last section. We need to start off by taking some matrix. So in this example, they give us a matrix here. And we need to program that matrix into the calculator like we've done in the previous two sections. So remember, the main menu that we are dealing with is accessed through second and x to the -1 down here. So second, x to the -1. Talked about this before. That brings you to the matrix menu. To edit the matrix in, you need to go over to edit. And I always choose A by default. Unless there's multiple matrices, then I just go in order. So I'll start off with A. Now you always have to specify what the size of the matrix is. This is a 3 by 3 matrix. There are 3 rows and 3 columns. And so we will go ahead and type in all of these as such. So again, this is going back to stuff we did in previous sections. We're inputting a matrix, programming a matrix into the calculator. From here, once we make sure everything's in here correctly, press second and mode to quit out of it, to go back to the main screen. Again, all familiar stuff. The new thing is, how do we find the inverse of that matrix now? We've programmed it into the calculator. And in fact, when we go back to the matrix menu, we want to call that matrix under names. And you should just have an A on your screen. Now to find the inverse, what you have to do is actually press x to the -1 by itself. If you do that, a little -1 pops up. So pretty much we're on step 3 here. Little -1's going to pop up. And you just press x to the -1 by itself. And when you press enter, this mess is what you should see on your calculator. If you obtain this mess, then you have at least found the inverse correctly. Now, of course, in my math lab, they would want something a little bit more refined. They would probably want this as simplified fractions. And so to convert all of these decimals to fractions, we actually did this before. And also I have it written down on the screen here. You press math, which is the 3rd button in the 1st column. It just says math. And you'll see convert to fraction. And if you do that, it will convert every one of those decimals to its corresponding simplified fraction. And if you did all of that correctly, you can move your cursor to the right to see the remaining entries. But if you typed in everything correctly, you should have obtained this matrix right here. And that is the inverse matrix. So that's how you find the inverse matrix in the calculator. So does anyone have any questions before we look at how to apply this information to cryptography? If not, then let's go ahead and move on to this idea of encryption. So cryptography is the study of encryption and decryption. So that just begs the question, well, what does encryption and decryption mean? So encryption, it's the process of encoding a message, and encoding is the process of disguising a message. So basically, if I want to send a message to somebody, and this is done all the time when you send your credit card information to Amazon, you don't just send your credit card number is not just sent as the number itself, because hackers are very good at what they do, and they can intercept messages that are sent from party to party. Instead, your computer takes your credit card number and disguises it using a very particular mathematical formula. And so it takes that, disguises your message, and then that's what it sends. And then if someone receives that in the middle, they will not be able to understand what the message means because they disguise your credit card number. It's the same idea here with messages. In fact, encryption and decryption has been around. One of the earliest reported cases of it, if anybody here is a history buff, Julius Caesar used Caesar cipher back whenever he did that. I'm not a big history guy, but that's one of the earliest reported cases of encryption, where he disguised his message by taking every character and shifting it to the right, I believe 3 or 4 places. So all the A's would become D's, B's would become E's, and so on and so forth. But we have a different encryption method here and decryption method. We use a matrix to encode. So we're going to use a matrix to disguise the message and a matrix to undisguise the message or to reveal the message. Now, when we encode a message, which means disguise it, we multiply the matrix by the matrix containing the numbers corresponding to the letters. So if we're sending a word, we want to convert that word into a number or a series of numbers. And then we put that series of numbers into a matrix and multiply that to the coding matrix. So that's how you disguise the message. To reveal the message or to decode, that's when we use the inverse. So you will see consistently, whenever I see the word decode, I will remind everybody that we want to use the inverse matrix. And so this process of converting a word or letters into numbers is simply going to be predicated upon these simple conversions here. So A is 1, B is 2, so on and so forth. The only additional thing to notice is that for a blank, we might use 0, we might use 27. It's going to be specified in the problem. So let's see this process because it's best seen in action. Now they give us a matrix and they call it the encoding matrix. Encoding means the matrix that we will use to disguise something. They want us to, we want to send the message cut, but we want to disguise this message before we send it. So the first thing we have to do is take the word cut and convert each letter to numbers. So C corresponds to 3, U corresponds to 21, T corresponds to 20. So that's the first step. But this is not encryption, because someone can easily see this sequence of numbers and think, all right, I could just change them back to letters. So we need to be more clever about this. And so from here, we need to take this encoding matrix, which was given to us as 3, 2, -1, 2, 1, 5, 3, -2, and 4. And we need to multiply that by the message as written as numbers, written as a matrix. Well, there's 2 different ways we could do this. We can write it as a row matrix or column matrix. The question is, which one do we use? Only one of these is going to make sense mathematically. Because if the right matrix is a 3 by 3, then that forces the number of rows for the second matrix to be a 3. in order for this multiplication to make sense. So we have to have 3 rows for the second matrix. Which one of these has 3 rows? It's not this one. That one has 3 columns. It's this one. So that is the matrix. So we will be using columns to represent our message, not rows, or else the matrix multiplication is not going to make any sense. So 3, 21, and 20. And now this is just simply a matrix multiplication that we can program directly into the calculator. Well, matrix, we can go ahead and program matrix A as the 3 by 3 matrix on the left. And then we can program the matrix on the right as matrix B. Second matrix is a 3 by 1 matrix. 3, 21, and 20 for the second matrix. Again, notice how the alignment of that second matrix is a column to match the alignment that we have in the notes here. They should not be left or right, or else the calculator will give you an error. And all we have to do is multiply matrix A times matrix B. Once you program the matrices into the calculator. What we obtain is the matrix 111, negative 13, and 182. Which means we wouldn't send out cut as 3, 21, and 20, because that's too easy. Instead, the encoded message is 111, negative 13, 182. That's what we would send out. That is the encoded disguised message. In fact, it's so disguised, 111 doesn't correspond to any letter. Negative 13 does not correspond to a letter. 182 does not correspond to a letter. This is on purpose. This is how well the disguise is. If you receive this, you have no idea how to reverse engineer it unless you know the key. It would be really tough for you to do so. So this is how we encode a message. This is how you disguise a message. Now, if we want to decode a message, so notice they switched the terminology on us to decode. And whenever you use, anytime you decode, you're going to use the inverse matrix. That's where that inverse stuff comes in to play. And the message that they want us to decode is 102, negative 15, 117. So imagine you're on the receiving end of this. Well, we need the encoding matrix that they gave us in the beginning, that we already have actually programmed into the calculator as A. We're going to take that matrix, but apply a -1 to it, because we are decoding. So notice I have a little -1 to the top right of the matrix. And the message we want to decode, 102, negative 15, 117. From here, we already have matrix A programmed into the calculator. So the only thing we have to do is program the new matrix B. This new matrix, I'm going to scroll down to matrix B. It's also a 3 by 1 matrix, but here it's consisting of 102, negative 15, and 117. So now we have matrix B in the calculator as 102, -15, 117. And now when we apply all of this in the calculator at once, we already have matrix A, but we have to click the inverse button. That will decode the message. Notice that little -1 symbol next to it. That decodes the message times matrix B. So we get 8, 9, and 20. And so the decoded message is 8, 9, and 20. So what this tells us, if we have a decoded message, that means we have something that is legible. As in, each one of these numbers can be converted to letters. And if you scroll up to the conversions of each letter to a number, you can quickly see that the conversion for 8 corresponds to H, 9 corresponds to I, and 20 corresponds to T. So the message is hit. So that is us decoding a message. So that's how this whole process works. Does anyone have any questions before we look at the next example? Okay, let's look at example 3 now. Example 3, they want us to convert the word technology from letters to numbers, and then we will be sending the encoded matrix. So the first step, whenever you send a word, we have to convert every character to numbers. So if you scroll up, you could see all the conversions there, or if you Google letters to numbers, you could probably find a quick table if you need one. A T is 20, E is 5, 3, 8, 14, 15, 14, 7, 25. I think I missed one. T, E, C, H, N is 14. Oh, I got L. 15 is O. There's 12, 15, 7, and 25. There we go. Okay, so there should be 10 characters here, or 10 numbers. And from here, we want to, they give us a new encoding matrix right here. So that encoding matrix always goes on the left. And we want to multiply to this matrix the word technology written as numbers. Now there's a problem here. So don't write this next part down. If you try to multiply this 2 by 2 matrix by the word technology written as a column, like we did in the last example, your calculator is not going to be happy with this. In fact, it's going to tell you that there's an error. The reason why the matrix on the left is a 2 by 2, and the matrix you just drew on the right would end up being a 10 by 1, because there's 10 characters in the word technology. There's 10 letters. So the 2 and the 10 don't match up. So you cannot use this matrix. In order for this product to make sense, you have to use 2 rows. So it says you have to use 2 rows. So you think, well, how do I use 2 rows? I have 10 characters. Well, we can, and so this is the part you can write down. We want to break up the word technology into pairs of 2. So now we would go column-wise, 20 and 5, but we can only have 2 rows. So we keep adding columns for each pair of numbers here. So that way we stick to having 2 rows. It doesn't matter how many columns we have. As long as we have 2 rows, then this product will make sense. So this is what happens when your message is too long for your encryption matrix. You have to break it up to where the product will make sense. So now we have a 2 by 2 and a 2 by 5. And the product actually makes sense now, which means we can plug this straight into the calculator. So with this matrix product, we have a 2 by 2 matrix that we can go ahead and plug in. 4412. And a 2 by 5 matrix for the second one. Once you plug all of those in, which takes a little bit of time to plug all of those in, it's just A times B. Get very expansive outcome from this. In fact, you might have to move your cursor to the right just to see everything. Move my cursor to the right to reveal the remaining ones. So the encoded message, the conclusion of this problem, this is what you would send out if you were sending this to somebody else who wanted this to be encrypted. You would read in the same order that we placed the letters, the numbers in. So that would be column down, and then we keep going to the next column and going down. You don't read it left to right, because that's not the order in which we placed the numbers in the very beginning. 30, then 44, then 19, and you keep going. So that would be the encoded matrix. Does anyone have any questions before we look at example 4? Yes.
Okay, so when the matrices match, well, how do you know if the matrices match up?
You mean if the product makes sense?
Yes.
Basically, it's always by this criteria right here. The product makes sense if the 2 inner numbers of their sizes are the same number. That's why if you wrote the word technology as one giant column, you would have 10 rows, but you're only allowed to have 2 rows.
Okay, that answers my question. Thank you.
Another way you can run into that not intuitively, but if you try to type it into the calculator and the calculator says dimension error, then that tells you I probably typed in one of the sizes incorrectly. That's another way you can run into that. You don't see it immediately. Let's look at another example and enforce this idea a little bit more. So example 4, they give us an encoding matrix A. And they tell us to use A inverse, or find A inverse. So there's actually two parts of this problem. And then with the inverse, decode the message, and they give us a collection of numbers here. So notice how they're saying with A inverse, use that to decode. You always use the inverse to decode every time. So they want us to find A inverse first. So A, they gave us as 3, 5, 1, and 2. So that's what we're going to find the inverse of. And this is exactly what we did at the very beginning of this section. So here, we need to program the matrix A into the calculator so we can find its inverse. 3, 1, oops, I messed that up. It's a 2 by 2 matrix, first and foremost, consisting of 3, 1, 5, and 2. So remember, to find the inverse, you have to go call the matrix under names, and then you click the inverse symbol. And so the inverse ends up becoming 2, -1, -5, and 3. So if anything, they're asking for what the inverse is, that's the inverse. That's how you do it in the calculator. So that's the first part. Next, they want you to decode the message. So you always, anytime you encode or decode a message, you're multiplying by some matrix. Here, the encoding matrix that they gave us was 3, 1, 5, 2, which we already have programmed into the calculator. The only difference is we have to apply an inverse to that matrix. You apply the inverse anytime you are decoding. But that's the only difference between encoding and decoding. And the message is the 57, 100, 20, 40, so on and so forth. The problem, just like we had in the last example, the 57, 100, 20, 40, all that, we cannot write that as one column because the multiplication, the matrix multiplication will not make any sense. So you have to break up the message because it's too large. This is a 2 by 2 matrix, which forces the number of rows for the right matrix to be 2, because those numbers have to be the same. So that tells us we have to split our message into groups of 2. 57, 100, 20, 40, 55, 92, 41, 73, 57, and 95. And now we know what the second matrix is. Now we know what we can go ahead and plug into. So it's a 2 by 5 matrix. I'll go ahead and just overwrite the numbers from before. This is matrix B, by the way. 55, 41, 57. Once I plug all of these values into the matrix, I have matrix A stored in the calculator already from when we found the inverse. And now what we're going to do is call matrix A. We're going to apply its inverse, because we are decoding, times matrix B. So notice the only difference between encoding and decoding is decoding has the additional inverse symbol. So we get 14, 15, 0, 20, 18, 1, 9, 14, 19, and 0. This is not the decoded message. The decoded message should be something legible. So decoded message, we have to read that from the matrix itself. We read it top down and then go to the next column. So I'm reading that information from the resultant matrix. And since we are decoding, this means that every number that we get should correspond to a letter. And if we look at that chart that associates letters and numbers, we would see that 14 corresponds to N, 15 corresponds to O, a 0, assume blanks correspond to 0. So this is a blank. It's just a space, means there's more than one word. And what this ends up coming out to be, it says no trains. That's the message. So that would be the decoded message here. Anytime you decode, your output should be something legible. Does anyone have any questions before we look at the next example? If not, let's move on to example 5. Encode the message math is fun using matrix A. So they give us an encoding matrix, and we need to multiply that by the message converted to, ultimately to numbers. I'm going to go ahead and skip the step of converting the characters to numbers, and instead I'm going to take those conversions and put them straight into a matrix. Now we have to, again, put this into groups of 2, because the matrix over here is a 2 by 2, which basically says we have to use groups of 2. So thinking about the phrase math is fun, the M in math is 13, the A in math is 1, then T is 20. So I'm going character by character here. The H is 8, but we can't forget about spaces because there's a different word now. And it says assume blanks correspond to 0. So after I type in MATH as 13, 1, 20, and 8 respectively, I put a 0 here for the space. The I is 9, S is 19, there's another space, so I use 0, F is 6, U is 21, and the N is 14. Now you might notice, well, now we're off by 1. There's not an even number of letters. So if that's the case, you can put a placeholder, just blank, a space, just so you can go ahead and fill in the matrix. But from there, we can go ahead and find the encoded message by typing this into the calculator. We need matrix A, we need matrix B, one, two, 1, 3. Matrix B seems to be a 2 by 6 matrix. We have an extra column here, 2 by 6. Then we can go ahead and type in those letters or numbers. And from here, we simply multiply A times B. I'm going to go ahead and skip to what the encoded message would be, how we read the matrix. 15, 16, 36, 44, 18, 27, 19, 19, 8, 69, 14, and one more 14. So that would be the encoded message. That's the intentionally disguised message that wouldn't make sense to anybody except for the person who knows the key to unravel this disguise. Okay. Let's look at example 6. Example 6, they give us, yet again, a coding matrix or an encoding matrix, same thing. And then they say the word encode, the word comb. Well, comb is just 3. The O is 15, the M is 13, B is 2. So our encoding matrix is -2, -3, -5, and 0. And we multiply that by the message we want to encode. But again, the message is too long for the matrix. So we have to split it up into groups of 2 again. This is a 2 by 2 on the left. And the 2 that represents the number of columns in the left matrix tells us how we have to group the rows of the right matrix. So this would be 3, 15, 13, and 2. Notice that's the letters of comb simply rewritten as numbers. But from here, the product is pretty simple. All we have to do is plug everything into the calculator. So that's -2, -5, -3, and 0 for the first matrix. The second matrix, it's a 2 by 2. It's 3, 13, 15, and 2. -81, -9, -36, and -39. So the encoded message is -81, -9, -36, -39. So that's what you would send out. Now, what about if you received a message and you wanted to decode it? So notice they even tell us, use A inverse to decode. And so with decoding, -2, -3, -5, and 0 was the encoding matrix. You have to find its inverse anytime you decode. The decoded message, or the message we want to decode, -80, -60, -102, -3. So we have a new matrix to program into the calculator. So matrix B is now a 2 by 2 matrix consisting of -80, -102, -60, and -3. And so now we do A inverse in the calculator times matrix B. And so we obtain the decoded message of 20, 8, 1, and 20. But since this is a decoded message, this means we should be able to convert this into a word or phrase of some sort. 20 corresponds to T, 8 is H, 1 is A, 20 is T. So it corresponds to the word that. Are there any questions before we look at the next example? For example 7, the encoding matrix is now larger than before. It's now a 3 by 3 that they give us. And they give us a very large encoded message, very large one. So quite a number of characters here. Like it might be 18. They tell us to use A inverse to decode the message. So they give us the hint, use A inverse to decode the message. Well, A, -1, -1, 3, 0, 1, -1, 1, 0, -1. The encoding matrix they give us, but we have to apply the -1 in order to decode. Notice I have the -1 symbol here. Now, in order to break up this encoded message, because again, the encoded message is one column is not going to work out. It's too large of a message. We have to break it up into groups. But we're not using groups of 2, like we've been doing in the previous examples. The reason why, this is a 3 by 3 matrix, which means now we have to break it up into groups of 3. So if you try to do rows of 2, your calculator will complain. So instead, you have to do groups of 3. -7, -4, and 30. And I'm just reading right off of the encoded message here. 5, -17, 34, 15, 7, -3, -2. So I believe this is 18 characters, and we want to see what this comes out to be. Or in other words, what is the decoded message from this? Well, first we have to program these 2 matrices in the calculator. Start off with matrix A, which is a 3 by 3 matrix. Okay, so matrix A looks good. Then we'll go to matrix B to plug in that giant matrix. The giant matrix seems to be a 3 by 6 matrix. And we can go ahead and plug in those values. It's quite a lot of typing. Like, let me make sure that everything is typed in correctly. So that's matrix B. And all you have to do is A inverse times B to get the decoded message. 15, 15, 12, 2, 5, 27, 28, 5. Again, it's 18 characters, so there's a good bit of numbers here. And all of these, because this is a decoded message, these all correspond to letters that we can quickly go ahead and decipher. First 5, 19 corresponds to S, 15 corresponds to O, 27 corresponds to a space. They do say assume a blank space is assigned to 27 at the beginning of the problem. So that's a space. What this ends up coming out to be is solve the exercise. Oops, S. Solve the exercise. That's the decoded message. And this is encryption and decryption using matrices.